Hello friends, so this is part 2 for the year 2023, and this we are going to solve 10 previous year questions, and all these 10 questions will be from the mains only. In the part 1 also we covered 10 questions from the mains. So first question, it states that 3 concentric spherical metallic shells X, Y and Z of radius A, B and C respectively with the order A less than B less than C have surface charge density sigma, minus sigma and plus sigma respectively. Shells X and Z have same potential. If the radii of X and Y are 2 cm and 3 cm respectively, the radius of shell Z is. So we are given as 3 shells. So we can just draw an approximate figure for that. So this is shell X, which is having a radius of A, and then we have our shell Y, which is having a radius of B, and finally we have shell Z, which is having a radius of C. So this is our X, Y and Z, and the charge density on X is given as plus sigma, on Y is our minus sigma, and on Z is also plus sigma. The radii of X and Y are given to us. It means value of A and B is given to us. We are given that our A will be equal to 2 cm and B is equal to 3 cm. And we are also given that the shells X and Z are at same potential. So you can say potential at shell X should be equal to potential at shell Z. So first of all, we are going to find out the respective charges on each shell. So therefore we can write that total charge on shell, let us start with our X shell, and we call that as Q of X, which will be equal to sigma multiplied by 4 pi a square. Next is our Y, we call that as Q of Y, which will be equal to sigma 4 pi b square. And finally we have our Z shell. Let us call this as charge as Q of Z. It will equal sigma 4 pi c square. We are given potential at Z is equal to potential at X. So we are going to use that condition. So we are given potential at X is equal to potential at Z, or we can write our V of X is equal to V of Z. We substitute the respective equations. Okay, and we need to find out what will be our first of all V of X. And here V of X means innermost shell. So innermost shell is going to have our potential that will be equal to summation of our Q of X Q of x divided by 4 pi epsilon naught a square plus Q of y is equal to 4 pi epsilon naught b, it's not square, plus Q of c 4 pi epsilon naught c. And we have to remember this V of x is the potential on the innermost shell. Similarly, we can write our V of z. V of z will be this is our outermost shell, so this will be coming as Q of x upon 4 pi epsilon naught c plus Q of y 4 pi epsilon naught c plus Q of z, here it will be z, Q of z and 4 pi epsilon naught c, here epsilon naught is missing. And we can just equate them. Therefore, we can write that our Q of x upon 4 epsilon naught a plus Q of y 4 pi epsilon naught b plus Q of z 4 pi epsilon naught c is equal to Q of x 4 pi epsilon naught c plus Q of y 4 pi epsilon naught c plus Q of z 4 pi epsilon naught c. And we already know the value of, okay, let us substitute value of Q of x, which is our Q of x is our sigma 4 pi a square. So we can write this as sigma 4 pi a square divided by 4 pi epsilon naught multiplied by a plus sigma 4 pi and this is b square divided by 4 pi epsilon naught b plus sigma 4 pi c square divided by 4 pi epsilon naught c. Okay. And similarly on the right side, we are going to get this as sigma 4 pi a square upon 4 pi epsilon naught c plus sigma 4 pi b square, and here we get 4 pi epsilon naught c plus sigma 4 pi c square divided by 4 pi epsilon naught c. And we can cancel out here sigma throughout. This sigma get cancels throughout. Similarly, we can cancel our 4 pi and the denominator also 4 pi epsilon naught get cancel out. Therefore, we are left with our a square by a plus b square by b plus c square by c is equal to a square by c plus b square by c plus c square by c. And we can write it as, this can be written as, okay, c we can take towards sorry, I missed one important part, that is B is having a charge density of minus sigma. So where is B? this B is our minus sigma, and here minus, and here also minus. This is our minus and this is also our minus. And this will be our A. So this A square cancel with A square, B goes with B, and C goes with C. And we get this as A minus B plus C. And on the right side, we take C as LCM. So this comes as A square minus B square plus C square. And C we can easily cross multiply. So this will be giving us as C A minus B, and this comes as plus C square is equal to A square minus B square plus C square. So this C square and C square cancels out, and we get this as C is equal to A square minus B square divided by A minus B. We can just open the denominator, A minus B into A plus B divided by A minus B. Here A minus B goes away. We are left with this A plus C. So we get our C is equal to A plus B, and that is A is given to us 2 or 3, 2 and 3. So this comes as 2 plus 3, giving us C is equal to 5 centimeters. So C, radius of cell Z, is our 5 centimeters. Next question. It states that the distance between the two plates of capacitor is D. Its capacitance are C1 when air is the medium between the plates. If a metal sheet of thickness 2D by 3 and of same area as the plate is introduced between the plates, the capacitance of the capacitor becomes C2. Then the ratio of C2 by C1 is. So here we are given a parallel plate capacitor and whose capacitance is given as C1 when it is air is the medium between the plates, and D is its thickness. So thickness of the plate is given as D. Now in this plate, in between the plates, a metal sheet of 2 by 3D is introduced. Okay, so if we introduce a sheet of thickness so this thickness is our 2D by 3. Now under this condition, the capacitance of the capacitor becomes C2. Okay. So which basically means that when the plate capacitor, when the metal sheet is introduced, the capacitor of this entire setup is given as C2. So this C2 is the, you can say, the capacitance of total capacitance, basically total capacitance. But within this area or this space is filled with air, and when air is present, we call this as so we are going to have two capacitances with metal sheet let us call this as C double prime, and this air, let us call this as C prime, and this distance will be equal to, thickness will be equal to d minus 2d by 3. So this comes as d minus 2d by 3, which will be giving us d by 3. So therefore this C2 is the total capacitance, and this total capacitance will be total capacitance, or we can say series combination of we can call this as C prime and C double prime. So we can easily find out our C prime. Our C prime is with respect to our air, and this comes as one second. Okay, so we can say our C prime will be equal to epsilon naught A, area is same, and this becomes as d by 3, because in this case air is the dielectric, and our C double prime will be equal to its dielectric one second, I'm missing something here. Okay, yes, this is a metal sheet. Okay, that was bad on my part. So let us sort it out again. Okay, so we are given that initially we are having a basic capacitor. Its capacitance is given as C1, and with A1 is a dielectric medium rather, and D is the distance between the plates, and A is the area of the plates. In this case we are given that the capacitance, let us call this as initial capacitance, and which is mentioned at our C1. So therefore we can write our C1 will be equal to epsilon naught A upon D. Now we are given that the thickness of metal sheet that is introduced is given as 2d by 3. So therefore from here we can calculate the remaining air gap. gap, and this remaining air gap will be equal to over d minus 2d by 3, which comes as d by 3. And it says that it is introduced in between the sheets, so we can presume that the sheet will be placed symmetrically. Therefore we can write that since the sheet is placed symmetrically, there are two air gaps on either side. Each of thickness will be equal to d by 6. So we can once again draw an approximate figure for that. So these are the plates of the capacitor, and in this plate symmetrically a sheet is being introduced. So this is the sheet, and the thickness of the sheet is given as 2d by 3. So please remember, this is a metal sheet. So this is 2d by 3. So either side of this we are going to have two air gaps, and each thickness width will be equal to d by 6, and this will be also a d by 6. Okay. So this entire thing is going to act as a two capacitors in series. Two capacitors in series, and the series capacitor plate area is same for the entire setup. So you can say plate area will be equal to A. Distance between the plates is d by 6. Distance between the plates is d by 6, and the dielectric medium is air. Dielectric medium is our air. We can also draw an equivalent of that. So this will be our leftmost plate of the capacitor, and this will be a plate which will be provided by the left part of this metal sheet. So this is going to provide us the other part of the sheet. Let me draw in the same color. So this will be our other part of the sheet, and this distance will be our d by 6, area is our A, and dielectric will be our air, and this will be our rightmost part, and the other part will be provided by this. So this will be our, and here also this distance is our d by 6, and this is our air as a dielectric, and area is same, and these will be connected by a connecting, that is because it is metal, so this will be a conductor. Okay. So now we get two capacitors which are having area is same and their distance between the plates is same. So we can call this, let us call this as C1, and this will be of C2. Obviously C1 and C2 will be equal because about them everything is same. Okay. And therefore these two are connected in series. Therefore we can say equivalent capacitance equivalent capacitance will be equal to 1 upon C equivalent is equal to 1 upon C1 plus 1 upon, sorry, not C1, let me name them different one. Because C1 is given to us, C2 is also given, so we can call this as C prime and C double prime, and these two will be equal with each other, C prime and C double prime, and we can write this will equal to twice C prime. Therefore, we can say our C equivalent will be equal to C prime oblique 2, and C prime we can easily write C prime will be equal to our epsilon naught A, area is same, and distance between the plates is our d by 6, and this goes by 3, so we get our C equivalent will be equal to 3 epsilon naught A by d, and under this modification, which is our C equivalent, the capacitor is said to be, capacitance is said to be called as C2, so this is our value of C2, and C1 we already found out, so we are just going to find out the ratio of their C2 by C1. So you can say C2 by C1 will be equal to 3 epsilon naught A divided by D, and C1 is a simple our epsilon naught A upon D, and this entire cancel out, so we get this ratio will be equal to over 3. Ratio of C2 by C1 is equal to 3. Okay, so we have to remember that the sheet is a metal sheet. Okay. Next question. It states that an electron revolves around an infinite cylindrical wire having uniform linear charge density 2 into 10 to the minus 8 coulomb per meter in a circular path under the influence of attractive electrostatic field as shown in figure. The velocity of the electron with which it is revolving is, it has to be 10 to the power 6. So we are given that electron is moving in a circular orbit about this cylindrical wire. Infinite linear charge density is given to us. Let us suppose that is our lambda. So therefore there will be a force at this point. Let us call this distance as small r. So here force will be equal to E multiplied by electric field. Therefore we can say electrostatic force on the electron let us call this as Fe will be equal to our charge multiplied by electric field, and electric field we already know is our lambda upon 2 pi epsilon multiplied by r. Now this force is going to provide us a required centripetal force. This force will provide the required centripetal force. Centripetal force, and the centripetal force is our m v square upon r. So we can just simply equate them, and we get this as our m V square upon R is equal to E multiplied by lambda divided by 2 pi epsilon naught R. And we are interested in velocity. So we can write this velocity will be equal to E times lambda divided by, we have this as 2 pi epsilon naught multiplied by m and its square root. We just substitute the values. We can say our velocity is equal to, charge is our 1.6 into 10 to the power minus 19. Lambda is given to us as 2 into 10 to the power minus 8. And we have this as 2 pi. Epsilon naught is our 8.85 into 10 to the power minus 12. Mass of electron is our 9.1 into 10 to the power minus 31. And its square root. So this will be coming approximately equal to 7.95 into 10 to the power 6 meter per second, which can approximate equal to over 8 meter per second. So we get this as 8. Next question. We are given that in this figure, the resistance of the coil of galvanometer G is 2 ohm. The EMF of the cell is 4 volt. The ratio of the potential difference across C1 and C2 is. So basically a bridge is given to us. And we have two capacitors C1 and C2. Two resistances 6 ohm and 8 ohm, and a galvanometer whose internal resistance is given as 2 ohm. So under steady state condition, the capacitor is going to act as an open circuit. You can see at steady state, capacitor, here are C1 and C2, acts as open circuit. So we can just redraw the figure, and we have our, from A we are having between B, and this galvanometer is having an internal resistance of 2 ohm, and this is our D. So we start with A, B, C and D, and we are given a supply voltage of 4 volt, and the capacitors which will be in between AC and BT, here was our C1 and here was C2, they will be acting as an open circuit. Therefore the current will be simply flowing this particular path. It will be going from A to B, B to C and C to D and back to the supply. Let us call this current as our I. And value is given to us as 6, we have here 2 and this is given as 8. Therefore we can write that the current I will be equal to supply voltage over 4, resistance is over 6 plus 2 plus 8. 6 plus 2 plus 8, which comes as 16. So this comes as 4 by 16, giving us 1 by 4 amperes. And we have to find out the potential difference across C1 and C2. For that, we should be knowing the voltage drop at C1 and voltage drop at C2. Voltage drop at C1 we can say is, let us suppose, our V1, and at C2 let us suppose that is our V2. So we can write that voltage drop across C1 drop across C1 which we called as V1, will be equal to voltage drop across point A and C. And between A and C, we can just remodify this particular circuit, and let me draw it like this. So this is suppose our point A. Point A is having a resistance between A and B, so this is a 6 ohm, and between B and C we are having a 2 ohm resistance, is C, and our capacitor C1 is connected in between, or not in between but across, that is connected across our A and C. So here we are having C1, which we said will be equal to our V1 voltage drop. So obviously that will be equal to voltage drop across AC, because it is entirely in parallel. And current flowing through the AC, which is our I, we already know its value is 1/4. So here 6 and 2 are in series. Therefore we can say our VAC will be equal to I multiplied by 6 plus 2. So we get our V1 will be equal to I is our 1/4, and this comes as 8, which gives us that a V1 is equal to over 2 volts. Similarly, we can do for our C2 also. Only difference will be that, let me draw it for C2 also. So for C2 is our across BC and D. So we start with point B, we go up till this is point B, we go up till C, and then we have resistance D. So this is 2 ohm, this is 8 ohm, and we are having our C2 is connected across our, which we called as V2, and obviously that will be equal to VBD. So you can say that the voltage drop across C2 voltage drop across C2, which we called as V2, and that will be equal to VBD. And here the current is our I, which is equal to 1/4. So we get this as I multiplied by 2 plus 8, and we get our V2 will be equal to 1/4 multiplied by 10, giving us 5 volts. And we have to find out the ratio C1 by C2, which means V1 by V2. Therefore we can say ratio C1 by C2, we are going to get this as 2/5. Sorry, this is my mistake. It's not 5 volt, but this will have a 5/2, okay, because this goes by 2 and this goes by 5. So we get C1, we found out is our 2, and this is about 5/2, which gives us as ratio is 4/5 volts. So this gives us ratio is 4/5. Option 2 is correct. Option 2 is correct. Next question. It states that an electric dipole of dipole moment 6 × 10⁻⁻⁶ coulomb meter placed in a uniform electric field of 1.5 × 10⁻³ Newton per coulomb in such a way that dipole moment is along the electric field. Work done in rotating dipole by 180 degree in this field will be millijoules. So we are given that we have to work done from 180. Initially it said that electric field and dipole moment are along. So in this case the angle between the dipole moment and electric field will be equal to 0. And in the second case we are already given it has to be 180. So therefore we can say work done on electric dipole, let us call that W, will be equal to dipole moment multiplied by our electric field, and this comes as cos of theta 1 minus cos of theta 2. Theta 1 is our initial angle. Initial means when dipole moment or electric field in the same direction. Therefore we can say our theta 1 is equal to 0, which tells us that cos of 0 will equal to 1, and secondly theta 2 is our 180 degree, which gives us cos of 180 will be equal to minus of 1. So we substitute the value, we get our work done is equal to dipole moment electric field 1 minus of 1, which comes as 2p times E, and both values are given to us. We substitute it, we get 2p is our 6 into 10 to the power minus 6. Electric field is our 1.5 into 10 to the power 3, and we get work done is equal to 18 into 10 to the power minus 3, which gives us 18 millijoules. So we have this as 18 millijoules. Next question. It states that electric potential at a point P due to a point charge 5 into 10 to the power minus 9 coulomb is 50 volt. The distance of P from the point charge is. So basically it is quite straightforward, directly based on the formula. We can say that the potential at point P, let us call that Vp, will be equal to K charge upon distance, that is our R. We need to find out our R. Therefore from here we can write our R will be equal to KQ upon Vp. K we know is our 9 into 10 to the power 9. Charge is given as 5 into 10 to the power minus 9, and voltage is given to us as a 50. And this is quite straightforward now. 10, 9, 10 and goes away. This goes by 10. So this will be coming as 0.9 meters, or we can say 90 centimeters. So option 3 is correct. 3 is correct. Next question. It states that a 600 picofarad capacitor is charged by 200 volt supply. It is then disconnected from the supply and is connected to another uncharged 600 picofarad capacitor. How much electrostatic energy is lost in this process? So we have two capacitors and they are of same value, but initially one is charged and another one is uncharged. Okay. Therefore we can say that we can divide this question into two parts. First is our initial condition. So under initial condition we are having two capacitors. Let us call this as C1 and C2. So this is our C1 and it's a charge to supply voltage of 200 volts. So let us call that as V1. And there is another capacitor, let us suppose that is C2, and it is okay, so it is charged. So obviously we are going to have initially some charge. Let us call this Q1. Q1 will be equal to C1 multiplied by V1. And let us call here the voltage as V2, obviously that is equal to 0. So from here we can say our Q2 is equal to 0. And we can find out our Q1. Q1 will be equal to our supply voltage is of 200 and this is 600 picofarad. So this comes 600 raised to minus 12 multiplied by 200. And this will be equal to 6 to 1.2 into 10 to the power minus 7 coulombs. So this is our Q1 and Q2 is equal to 0. So total initial charge let us call that Qi. Qi will be equal to Q1 plus Q2. Obviously that will be equal to 1.2 into 10 to the power minus 7 coulombs. Now we come to the final condition. And final condition. So in the final condition, we can say the capacitors are connected. Capacitors are connected. So we can write that if their capacitors are connected, they are going to have, we can say, the initial charge and final charge is to be same. And you can say that final total charge will be equal to initial total charge. Initial total charge. So we can say our Q final will be equal to Q initial, which is our 1.2 into 10 to the power minus 7 coulombs. And the equivalent capacitance let us call this as C equivalent, and the C equivalent will be equal to C1 plus C2. These are same, so this comes as 2C1, and we can write this will be over 2 into 600, giving us 1200 picofarad. So now we can find out the final voltage. Final voltage, let us call this as Vf, will be equal to our final charge divided by C equivalent. Final charge is our 1.2 into 10 to the power minus 7, and this comes as 1200 into 10 to the power minus 12. So we get this final charge will be equal to our, final voltage will be 100 volt. And we are interested in energy lost. So let us find out initial energy also. So we can say initial energy, and this initial energy will be only dependent upon C1 because this is only having the charge stored. So we can say our U of I will be equal to half C1 V1 square. So this comes as half C1 is our 600 into 10 to the power minus 12. V1 is our 200 whole square. So we get UI initial will be equal to 12 microjoules. Now we can find out our final energy. final energy, let us call this UF, will be equal to half CE, and we have here VF square. C equivalent is our 1200 picofarad minus 12, and VF is our 100 whole square. So we get our final energy is equal to 6 microjoules. We have to find out the energy lost. Energy lost will be equal to our U initial minus U final, which gives us 12 minus 6 is equal to 6 microjoules. Energy lost in the process is 6 microjoules. Next question. We are given a parallel plate capacitor with plate area A and plate separation D filled with dielectric material of dielectric constant K is equal to 4. The thickness of dielectric material is X, where X is much less than D. Let C1 and C2 be the capacitance of the system. For X is equal to 1/3 of D, and it is X is equal to 2D by 3. And here this is one third of the D, respectively. If C1 is equal to 2 microfarad, then the value of C2 is. So here we are given that the thickness of dielectric is changed. In the first case, thickness of dielectric is D by 3. In the second case, it is 2D by 3. Respectively, their capacitance are given as C1 and C2. So we can write that for X is equal to D by 3, our capacitance, that is C1, its value is given as 2 microfarad. And when our X is equal to 2D by 3, capacitance value is given to C2, and which we are supposed to find out. And in the both cases, dielectric is same, so value of dielectric constant is given as 4. Also the width of dielectric is same, therefore the width of this air will be equal to D minus X. So here we are going to have two capacitors, and one capacitor is of thickness of X, another is our D minus X. So let us call this as D minus X as C prime, and this we are going to call as C double prime. C double prime we can later on replace with C1 and C2 as per our requirement. So we can say that two capacitors are in series. Two capacitors are in series, and these capacitors are, you can say, with air as dielectric, and we call this as C prime, and next is with a dielectric medium, and we call this as C double prime. And for C prime, the thickness is our D minus X, and for C double prime, the thickness is our X. Therefore we can say the total capacitance let us call this as C equivalent will be equal to 1 upon C prime plus 1 upon C double prime. And C prime is with respect to air. Therefore, we can write this as 1 upon C equivalent will be equal to C prime is for our air. Therefore, we can write this as epsilon naught A, and distance is our d minus x, plus C double prime is with respect to our dielectric, and area is also same in this case, but dielectric constant is K, and width or thickness is our x. So we can take 1 upon epsilon naught A as common. So this comes as d minus x plus x upon k. So from here we can find out our C equivalent. C equivalent will be equal to epsilon naught A, and this comes as d minus x plus x upon k. Now we can divide this C equivalent into two parts. Sorry, not into two parts, but we can define it accordingly to the values of the thickness, that is our x is equal to d by 3 and x is equal to 2d by 3. So in this case, one second. Okay, the C1 and C2 are given as a capacitance of the system. It means the C equivalent will be called as C1 when the value of x is equal to d by 3, and the C equivalent will be called as C2 when value of x is equal to 2d by 3, because C equivalent is the capacitance of the system. So we are going to modify the C equivalent according to the value of x. So in the first case, we get this as C1. So C1 will be equal to epsilon naught A, and this comes at d by 3 plus x by k. And we can solve it. This will be coming as our epsilon naught A, this will be our 2d by 3, and this will be our x value of, sorry, I forgot to put here value of x. This will be our d by 3, and it comes as d by 3 k. Okay, so we can just solve it further. We get this as C1. We can take d as common, and we get this as 1 by d, and we can also take, one second, C1 is given to us. Okay, because C1 is given to us, we can just substitute the values. Let me write it. We can just find out the ratio. We can sort it out later on. 2d by 3 plus d upon 3k. So this is our C1. Similarly, we can find out our C2. C2 will be our epsilon naught A, and this comes at d minus 2d by 3. Now the value of x is 2d by 3 plus 2d by 3k. And once again we can take d as common. So this will be coming as epsilon naught A divided by, this will be our d by 3. Sorry, not d by 3, but 1 by 3. Here also 1. And this comes as 1 by 3 plus 2, 3 by k. So let us take the ratio of C2 by C1. C2 by C1, and C2 we have 1 upon D, and this comes as epsilon naught A upon 1 by 3 plus 2 3 times K, and this also is 1 by D, and we have epsilon naught A, this comes as 2 by 3 plus 1 by 3 times K, and from here epsilon naught A cancel, D and D goes away. Similarly, this 3 also cancels out throughout, and we are left with our this will be over 2 plus 1 by K and divided by 1 plus 2 by K. Value of K is given to us as 4. Therefore, we substitute it. We get this as 2 plus 1 by 4, and this is 1 plus 2 by 4. So this comes as 8. 8 plus 1 is 9. And this comes as 4 plus 6, that is 6 by 4, which gives us 9 by 6. C2 is given to us as 2. So therefore, we can write, C1 is given to us 2. So C2 will be equal to C1 times 9 by 6, which is 2 times 9 by 6. And 6 goes by 3, 9 goes by 3. So this C2 will be our 3 microfarad. So value of C2 is 3 microfarad. Next question. It states that a dipole comprises of two charged particles of identical magnitude Q and opposite nature. The mass m of positively charged particle is half of the mass of the negative charged particle. The two charges are separated by a distance L. If the dipole is placed in a uniform electric field E such that dipole axes make a very small angle with the electric field, the angular frequency of the oscillations of the dipole when released is given by. In normal question of dipole, we always take our mass as well as charge is to be same. Charge will be opposite obviously, but in this particular case the charges are no doubt opposite, but the mass is half of the other. Okay. So if we are having same charges, so let me plot an approximate figure for that. So we are having, this is our suppose minus Q, and we have charge of plus Q at the other end, and our electric field is towards right. Okay. Now we are given that the mass m of the positively charged particle is half of the mass of the negative charged particle. Okay. So it means mass of the positive charged particle is half of the negative charged particle. Therefore, we can say that mass of negative charged particle is over 2m, and for positive it is m. Under normal circumstances, if both sides are having mass m, then the moment of inertia will be, you can say, lying exactly at the center. But in this case, it will be little bit shifted towards the minus of Q. Let us suppose this is the point of our center of mass. Sorry, not moment of inertia, but center of mass. And this dipole is going to, you can say, oscillate along about the center of mass. Okay. So this is our center of mass. So this is the important part here. We are going to find out the respective distances. We can do that later on also. Okay. And total length is given to as our L. So we can say that the dipole moment which is our P is equal to Q and L, and you can just write it as QL. Now we are given that it is making a small angle theta, so obviously it will, let us suppose, something like this, small angle theta, okay, and therefore you can get torque equation. Torque equation will be our tau is equal to our dipole moment across our electric field, which we can write as PE sine of theta. As stated, theta is small, therefore we can put sine of theta is approximately equal to theta, so we can write our torque is equal to PE times theta, and this torque is going to provide the angular acceleration. This torque provides angular acceleration. Therefore, we can write that our tau is equal to moment of inertia times angular acceleration, or we can write this as I double derivative of our theta with respect to time. Therefore, we can say our PE theta is equal to moment of inertia I double derivative of our theta, and we can write, okay, so this will be restoring torque, so therefore we can put here minus. So we can write the equation will be equal to our d square theta upon dt square plus PE upon I multiplied by theta is equal to 0, which is a standard equation for simple harmonic motion. Equation of SHM. Therefore, we can write that our omega square is equal to dipole P multiplied by E divided by I, or we can say P we know is our QL times E divided by I. This is our angular frequency. Now we are going to substitute value of moment of inertia. Okay. And let me draw this figure here. So we are having minus Q, mass is 2m, plus Q, mass is m, and the center of mass is somewhere here. Let us call this as R2, and this distance of R1. And for the sake of convenience, let us say this point, we call this as our origin having coordinates 0, 0. Okay. We'll say that let center of mass be the origin. Okay. You can take any coordinate, but origin is going to solve us this quite easily, because we have to find out this R1 and R2. Okay. So let the center of mass be the origin, and distance of minus Q is our R2, and plus Q is our R1 from the origin. So we can easily write that our MR1 is equal to twice MR2, which gives us R1 is equal to twice R2, and R1 plus R2 is our L. R1 plus R2 is equal to L. So using this equation, we can easily find out value of R1 as well as value of R2. So we are going to get from here that our value of R1 will be equal to 2L by 3 and value of R2 will be equal to L by 3. So we are going to find out moment of inertia about the origin, which is center of mass. Therefore we can say that moment of inertia which is I about center of mass, or we can say our origin. So we can say our I will be equal to mr1 square plus twice mr2 square, and we substitute value of R1 and R2. We get this as m, and we have this as 2L by 3 whole square plus twice m, and this is L by 3. Once again, sorry, R2 is L by 3. Yeah, it's correct. R1 is 2L by 3 plus m. It's correct. And this will be giving us m. We can take common. We are going to get this as 4L square by 9 plus this comes as 2L square by 9. So it comes as 4 plus 6L square by 9, and divided by 6L square by 9. So this comes as m 6L square by 9. So this goes by 3 and goes by 2. So we get moment of inertia will be equal to 2 by 3 ml square. So we found out value of our I. Now we can just substitute it in the angular frequency, that is omega, which was our QLE divided by moment of inertia, and we get this as QLE. This is our 2 by 3, and this we have ml square and its square root. This square goes by L, and this is already in simplified form. So we get this as 3 by 2 QE divided by ml. So this is our angular frequency. Okay, so the only minor, you can say, twist they have made, they have changed the mass. So if your mass is changed, the position of center of mass will be shifted. So accordingly, the moment of inertia, that is value of I, is going to change. Next question. Here given, as shown in the figure, two parallel plate capacitors having equal plate area of 200 centimeter square are joined in such a way that A is not equal to B. The equivalent capacitance of the combination is X epsilon naught times Farad. The value of X is. So let me draw the figure. So the basic figure is distance between, this is A, this is B, and this distance is given as D, and this distance is given as C, and these two plates are connected like this. And I think this is all given to us. and this will be the external connection to the plates. So basically here we are having two capacitors and which are connected by a conductor. So let us suppose this is our C1 and this is our C2, and in between the conductor whose thickness is given as our C. So we can say that the thickness between the plates is C, therefore we can write that A plus B plus C is equal to D. So we can write from here that A plus B plus C is equal to D, and we can say our A plus B is equal to D minus C. Value of D and C is given to us. Value of D, it is given as 5 into 10 to the power minus 3, and value of C is given to us 1 into 10 to the power minus 3. So we substitute it, we get this as 5 minus 1 into 10 to the power minus 3. So this gives us that our A plus B is equal to 4 into 10 to the power minus 3. And here we have to keep in mind that it is given that A is not equal to B. Okay, we will sort out that later on. Now we can easily find out the value of capacitance C1. So we can say our C1 will be equal to epsilon naught A, and distance between the plates is given as small a, and we can say our C2 is equal to area is same and distance is given as B. These two capacitances are connected in series, so we can say our C equivalent capacitance let us call this as C equivalent. So we can write 1 upon C equivalent is equal to 1 upon C1 plus 1 upon C2. So this comes as epsilon naught A, and this comes as epsilon naught A and B. So we get this as epsilon naught A, and this we have A plus B, whose value we already know. Therefore we can write that our C equivalent is equal to epsilon naught A divided by A plus B, or which we can also write as epsilon naught A upon D minus C. These are one and same thing. We substitute the value, and this is our 8.85 into 10 to the power minus 12 into area is same 10 to the power minus 2, and D minus A or A plus B we found it 4 into 10 to the power minus 3. So we got that our C equivalent will be equal to 4.427 into 10 to the power minus 11 farads, and this is given to us as x times epsilon naught. Okay, we should not have put the value of epsilon naught anyways, and we need to find out our x. So therefore we can say our x will be equal to C equivalent is our epsilon naught A upon A plus B is equal to epsilon naught times x. Epsilon naught cancels out. We get from here that our x is equal to A upon A plus B. A is our 2 into 10 to the power minus 2, and A plus B is 4 into 10 to the power minus 3. And this goes by 2. This comes as 0.5. 0.5 is 10, and this comes as x is equal to 5. Okay, I should not have put the values. So value of x is equal to 5. This question was also asked here in 2000, you can say 23 only. In this part we solved it initially, where it was given that this entire gap is filled by a metal sheet. Okay. And we solved it in almost same way, not exact way, but the basic premise of the question was same. So I think this was the, yes, so this was the part second for the year 2023, and in part second also we solved 10 questions. All these 10 questions were from the mains question. In the part 1 also we solved 10 mains question. Hopefully in the part 3 we are going to complete this 2023 questions consisting of both mains as well as advanced. Hopefully the part 4 won't be required. Okay, if required, then we are going to move to part 4 also. So this completes all the 10 questions from the year 2023 in part 2. Thank you.